Hello everyone, this is Roger. Today I'll discuss to you motion in 2 or 3 dimensions. I hope I could make this topic easier for you. Before we'll start our topic, let's review on vectors. You should master vectors in order for you to solve problems involving motion in 2 or 3 dimensions. We all know that vector is a quantity with magnitude and direction. And the symbol for a vector is a letter with an arrow on the top. This vector A is represented by this blue arrow. Okay. The length of that arrow is the magnitude of our vector. And the angle theta indicates the direction of our vector. Now this vector A has a components AX and AY. Now, what is the formula in finding AX and AY? If the angle theta of vector A is measured from the positive x-axis, meaning this angle here, then our AX is equal to A cosine theta because AX is in the adjacent side of our angle theta. That's why AX is equal to the magnitude of A times cosine theta. And AY, since it is in the opposite side of our angle theta, then AY is equal to A sine theta. Now, it is not always the case that AX is equal to A cosine theta and AY is equal to A sine theta. Depending also on the quadrant, AX and AY could be negative or positive. For example, in this first quadrant, both AX and AY are positive. While in the second quadrant, AX is negative, so instead of AX equals A cosine theta, on the second quadrant, AX should be equal to negative A cosine theta and AY is equal to A sine theta. Now in the third quadrant, both of them are negative. So AX should be negative A cosine theta and AY is equal to negative A sine theta. And in the fourth quadrant, AX is positive, so AX is equal to A cosine theta and AY is equal to negative A sine theta. Now to get the angle theta, given the value of our AX and AY, we'll use the trigonometric function arctan AY over AX. Since our angle is measured from the x-axis, there's only 4 ways to name our angle. So that is north of east, meaning from east moving to north, so that is north of east, or the first quadrant is north of east, and the second quadrant, that is north of west. In the third quadrant, south of west, and the fourth quadrant is south of east. Now, if the angle theta is measured from the y-axis, so we are talking of this angle theta. So again, same vector A, but our angle is from the y-axis. So now, what is the value of our AX and AY? From our trigonometry, we know that the adjacent side is the cosine and the opposite side is the sine theta. So AX now is equal to A sine theta and AY is equal to A cosine theta. So opposite, adjacent. Okay, A sine theta, A cosine theta. Again, depending on what quadrant, AX and AY could be positive or negative. So in the first quadrant, you have AX is equal to positive A sine theta and AY is equal to A cosine theta. The second quadrant, your AX is equal to negative A sine theta, and your AY is equal to A cosine theta. In the third quadrant, both of them are negative, so AX is equal to negative A sine theta, and AY is equal to negative A cosine theta. And in the fourth quadrant, AX is equal to A sine theta, and AY is equal to negative A cosine theta. And to get the angle on the y-axis, we'll use arctan AX over AY. So you only have 4 ways to name if the angle is measured from the y-axis. So that is east of north, okay, meaning from north moving to the east, so east of north. On the second quadrant, that is west of north. On the third quadrant, that is west of south. You will know that the angle is created on the x-axis or y-axis depending on the last direction that it mentioned. If the last direction is north or south, so meaning your angle is created on the y-axis. But if the last direction mentioned is east or west, so that is created on the x-axis. Now, to find the magnitude of our vector A, we'll use a Pythagorean theorem. So it's just square root of ax squared plus ay squared. Let's review on rectilinear motion. So we have here a person moving from x naught to x final. The displacement of that person moving from x naught to x final is represented by this delta x with an arrow on the top. So meaning displacement is a vector, which is equal to the final position xf minus the initial position x naught. Okay. So since displacement is a vector, if the value is positive, then it's moving to the right, and if the value is negative, it's moving to the left. Now, when a person moves from x naught to x final, it consumes time. So the time it consumes is what we call the time interval delta t, where delta t is equal to t final minus t initial. And if we divide that displacement with the time interval, so we have the average velocity. So average velocity is just displacement over time, or delta x over delta t, or x final minus x initial over t final minus t initial. So every time your velocity change, will have a acceleration, and the average acceleration is equal to v final minus v initial over delta t. So that is the average acceleration. So we call that average because we have a time interval. And when we say instantaneous velocity, so that is the velocity at that moment or at that instant. Meaning, our time interval is so small, that's why we have the instantaneous velocity. For example, if you are looking at your speedometer at that instant or at that moment, given a direction, so that is your instantaneous velocity. And also the instantaneous acceleration is your acceleration at that moment or at that instant. Okay. So the difference between average and instantaneous is that average has longer time interval and instantaneous is a very small time interval which approaches to 0. Now let's go to our main topic, the position in 2 or 3 dimensions. In rectilinear motion, the position is represented by x naught and x final. So The difference in 2 or 3 dimensions is that the position P of an object in 2 or 3 dimensions is described by x, y, and z coordinates. Okay, and we'll use a vector notation. Okay, so the position P of an object is the position vector r equals x I hat plus y j hat plus z k hat. So in 2 dimensions, for example, we have here an object at point P located at the coordinates x1, y1. So this is x1, y1. And the length of this position vector is equal to the square root of x1 squared plus y1 squared. In vector notation, our position vector is equal to r1 equals x1 I hat plus y1 j hat. In 3 dimensions, the magnitude of r1 is equal to the square root of x1 squared plus y1 squared plus z1 squared. The position vector in 3 dimensions, we have r1 equals x1 I hat plus y1 j hat plus z1 k hat. Now let's go to the displacement in 2 or 3 dimensions. In rectilinear motion, the displacement is represented by delta r, which is equal to x final minus x initial. So meaning from point x naught to point x final. Now in 2 or 3 dimensions, suppose that an object moves from point P to point Q during a time interval t1 to t2, then our displacement delta r in 2 dimensions is just equal to the difference of the position vector. So instead of x final minus x initial in rectilinear motion, we have the position vector r2 minus r1. So this is our r2 minus r1. Our r2 has a component x2 I hat plus y2 j hat, and our r1 has the components x1 I hat plus y1 j hat. Now we group the I hat, so that is x2 minus x1, and in the j hat we have y2 minus y1. So our displacement is just the displacement along x plus the displacement along y. Now in 3 dimensions, we have similar pattern. We have r2 minus r1, except that our r2 now has a z component, z2 k hat, and our r1 has z1 k hat. Again, we can group the components with I, j, and k. So we have here x2 minus x1 I hat, y2 minus y1 j hat, and z2 minus z1 k hat. So it's just the displacement in 3 dimensions is the displacement along x plus displacement along y plus displacement along z. Now let's go to the velocity in 2 or 3 dimensions. In rectilinear motion, the velocity is just the displacement over the time interval, or delta x over delta t. Now, in 2 or 3 dimensions, the average velocity of the particle moving from point P to point Q is equal to delta x over delta t. So this is 1 dimension rectilinear motion. In 2 dimension, we have delta y over delta t plus delta z over delta t for 3 dimensions. So it's just the average velocity along x plus average velocity along y plus average velocity along z. And the instantaneous velocity is just the limits of your average velocity as delta t approaches 0, meaning instead of delta t we have now dt. So that is dr over dt is our instantaneous velocity. And it's just dx over dt I hat plus dy over dt j hat plus dz over dt k hat. So meaning our instantaneous velocity is just our velocity along x plus velocity along y plus velocity along z. Now let's go to the acceleration in 2 or 3 dimension. Remember, the acceleration occurs when there is a change in velocity. Okay. In rectilinear motion, our average acceleration is equal to the change in velocity over the time interval. Now in 2 or 3 dimension, the average acceleration of the particle moving from point P to point Q is equal to the change in velocity over change in time, or v2 minus v1 over delta t. Since our delta v, or change in velocity, is just the change of velocity along x over delta t plus our change in velocity along y over delta t plus change of velocity along z over delta t. So our average acceleration is just the average acceleration along x plus average acceleration along y plus average acceleration along z. Now in instantaneous acceleration, it's the limits of the average velocity as delta t approaches to 0. Meaning instead of using delta t, we use dt. So dv over dt, that is our instantaneous acceleration. And it's just the dvx over dt I hat plus dvy over dt j hat plus dvz over dt k hat. And or you can use second order derivative, or your instantaneous acceleration is just ax I hat plus ay j hat plus az k hat. So we are done with the discussion in position, displacement, velocity, and acceleration. Now let's discuss projectile motion. So every time there's a ball game, it encounters a projectile motion. Okay. Example, throwing a ball, a basketball, or in a football, or playing Angry Birds, Pokemon, or archery. But what is projectile motion? Now, it's a motion of any object or body that is given an initial velocity and then follows a path determined by the gravitational force acting on it and by air resistance. But in our discussion, we will neglect air resistance since it makes the problem more complicated. So we knew that a projectile motion follows a path determined by a gravitational force. So what do you call that path? So the path is what we call trajectory. It's the path followed by the projectile. It's a parabola. Here's an example of a projectile motion. It's the trajectory is a parabola. So what are the characteristics of a projectile motion? So one of the characteristics of a projectile motion is that it has a constant vertical acceleration or free fall. So this is an example of a free fall, constant acceleration. So throwing a ball upward or downward or dropping a ball is a free fall, and it has a constant vertical acceleration. So this is a free fall motion. So that is one characteristic of a projectile motion. In order for this to be called a projectile motion, you must have a constant horizontal motion. Okay, so you have a constant speed along x, or you have zero acceleration along x. looking at our trajectory, from the start we have an initial velocity, and this initial velocity has a components of v naught x and v naught y, and v naught x is just equal to v naught cosine theta, and our v naught y is equal to v naught sine theta. Again, depending on where you measure the angle, if you measure the angle on the y-axis, then your v naught x is equal to v naught sine theta, and your v naught y is equal to v naught cosine theta. Again, depending also on what quadrant, they could be positive or negative. So that's why you need to review on vectors. So now let's go to the equations of motions of a projectile. And it can be divided into two, that is the horizontal motion and the vertical motion. On horizontal motion, we know that the acceleration along x is equal to 0. Then equation 1 and equation 4 will reduce into Vx is equal to V naught x. Equation 2 and equation 3, since our acceleration is 0, will be reduced to x final is equal to x naught plus V naught x times time. So meaning the final position of x is equal to the initial position of x plus the initial velocity along x times time. So you only have to memorize two equations in horizontal motion, that is Vx is equal to V naught x and x is equal to x naught plus V naught x t. The vertical motion of the projectile has a constant acceleration, and we know that acceleration is equal to negative 9.8 meter per second squared, which is our acceleration due to gravity. But instead of ay equals negative 9.8, we use ay equals negative g, where g is equal to 9.8 meter per second squared. Okay, we use this so that it's easier for us to rearrange our equation. Now in equation 1, we have final velocity of y is equal to the initial velocity of y minus the gravity times time. So this equation involves only final velocity, initial velocity, and time. Now in equation 2, we have a position, final position y can be determined if you know the initial position y naught plus the initial velocity of y times time minus 1/2 gt squared. So on the equation 2, it involves position, initial velocity, and time, meaning the final velocity is missing in this equation. Equation 3 is final position y equals initial position y naught plus 1/2 times final velocity vy plus initial velocity vy times t. Equation 3 is without acceleration. And equation 4, we have final velocity vy squared, which is equal to the initial velocity y squared minus 2 times the gravity times the displacement along y. So in equation 4, it does not involve time. Okay, in solving problems, we will use these equations depending on the situation of the problem. And V naught x is equal to V naught cosine theta, and V naught y equals V naught sine theta. Again, depending on the angle theta. This is not always the case. To solve the problems involving projectile motion, you need to memorize these equations. As you can see, the y component in this free fall is the same as the y component of this projectile, and the y component is independent with the x component. The only variable common to the x and y component is the time. Okay, they only intersect at the value of time. So meaning the time in y is equal to time in x, meaning the time it falls is the same as the time it travels from here to here. Okay, you should remember that. So now let's solve the equation of a projectile. So we have here a trajectory. Okay, the shape of this trajectory is a parabola, so we expect that our equation should be a parabola. So at any given time t, the position, okay, at any position x and y position of this trajectory is given by the equation x is equal to v naught x times t and y equals v naught y minus 1/2 gt squared. Sorry for this plus sign. So although it's same, but it should be negative 1/2 gt squared. So now let's solve the equation of a projectile. So we all know that the trajectory of a projectile motion is a parabola, so we will expect that our equation is a parabola. And at any given time, the position of the projectile, for example here, our x is determined by the initial velocity along x times time, and our y is determined by the initial velocity along y times time minus 1/2 gt squared. And our t from x equals v naught x is equal to x over v naught x. And v naught x is our x component of our velocity v naught. So therefore, our x is equal to v naught cosine theta. And the value of this t will be substituted in the y. Okay, so our equation becomes from y equals v naught yt minus 1/2 gt squared. It becomes v naught y, which is v naught sine theta, is the y component of our v naught, times time, which is x over v naught cosine theta, minus 1/2 g times t squared, which is x over v naught cosine theta, okay, squared. So we'll cancel v naught, and our sine theta over cosine theta, which is here sine theta over cosine theta multiplied by x. So x sine theta over cosine theta minus, okay, it's same, x squared over v naught squared cosine squared theta. So the equation is equal to y equals x tangent theta, which is sine over cosine tangent theta, minus g over 2 v naught squared cosine squared theta times x squared. So now let's solve for the time for maximum height of a projectile. We have here a trajectory, and this object has an initial velocity at an angle theta, and when an object reaches this position, it has the maximum height. So how will we determine that an object is at the maximum height? So there's only one condition, that is our final velocity Vy should be equal to 0. That is the position where an object is at the maximum height. And also the horizontal velocity should remains the same. Let's use the fourth equation. 0 equals v naught squared plus 2ay h max, or minus 2gd. So we can rearrange this equation, and our two ay h max is equal to negative v naught y squared. And our v naught y squared is just the y component of our v naught squared sine squared theta. Okay, so our h max is equal to negative v naught squared sine squared theta over 2ay. Or we can replace this one by h max equals v naught squared sine squared theta over 2g. And to calculate the time, we need equation 1. Okay. So using equation 1, the time needed for the projectile to reach the maximum height is 0, since our final velocity is 0 at the maximum height, then equals v naught y plus ayt or minus gt. And ayt is equal to negative v naught y, so we just rearrange this one, and we know that the v naught y is equal to negative v naught sine theta. The time to reach the maximum height is equal to negative v naught sine theta over ay, or t is equal to v naught sine theta over gravity. So now let's calculate the maximum range of a projectile. So when we say maximum range, is that from this position, the initial position, up to this final position. Okay, meaning if an object starts from the ground, which is y equals 0, then it should end with y equals 0. So meaning our initial position and final position of y should be equal to 0. So the equation now, y equals y naught plus v naught yt plus 1/2 ayt squared becomes 1/2 ayt squared equals negative v naught y times t. So the time it took from this point up to this point, or the time it took for the maximum range to occur, is equal to t equals negative 2v naught sine theta over ay, or t equals 2v naught sine theta over g. Now, the only common with x and y components of a projectile motion is the time. The time it took for this object to return from the initial position along y is the same as the time it took for the maximum range. Now, at the maximum range, we'll use this formula x equals v naught x t, and our t is equal to the value here, and our v naught x is equal to our v naught cosine theta. And when we multiply this one, we have negative 2v naught squared cosine theta sine theta over ay. Remember, sine 2 alpha should be equal to 2 sine alpha cosine alpha. Okay, so this equations now becomes v naught squared sine 2 theta. So the 2 cosine theta and sine theta is replaced by sine 2 theta. So the maximum range is equal to negative v naught squared sine 2 theta over ay. The final velocity of y here is equal to the negative of initial velocity of y here. Projectile motion at various initial angles. This figure summarizes what will happen if you vary the initial angle. In terms of maximum height, increasing your angle will also increase the maximum height up to 90 degrees. Okay, because of this equation. And also the time it took for the projectile motion to occur is when you increase the angle, you also increase the time it took for the projectile motion to reach back to the ground. For the maximum range occurs at 45 degrees. Okay, since this is sine 2 theta, meaning sine 2 times 45 is 90, so sine 90 is the maximum value for this sine theta. Adding 15 or subtracting 15 from 45 degrees, for example, we have here 60 and 30, they have same range, okay? And adding or subtracting 30 degrees, we have 15 and 75, so they have the same range, okay? So now let's start to solve problems involving projectile motions. If you listen carefully and follow all the steps, you can solve any problems involving projectile motions. And this topic is very easy for you now. Okay, so let's start. Now we have here a problem: a military helicopter on training mission is flying horizontally at a speed of 60 meters per second and accidentally drops a bomb at an elevation of 300 meters. The first question is, we have how much time is required for the bomb to reach the earth. Okay, so step 1, or the first technique, is to know what is the unknown. So the question is how much time. So our unknown is time. Okay, so what will we do is to look for our formula that involves time. Now I will look at my sheet. Okay, formula. Okay. Okay, I will check all the equations that involves time. So we have here we have time, here, and here. So we have 4 choices. Now let's go back to our given. So we have an initial velocity of, so since it is flying horizontally at a speed of 60 meters per second, so this is our horizontal velocity v naught x, which is equal to 60 meters per second. And we also have an elevation of 300 meters. So our y naught is equal to 300 meters, and our final y should be equal to 0, since it should reach the ground. Okay, and also we have here a hidden given, and that is if you drop an object horizontally, meaning you have no initial velocity along y, so you have v naught y equals 0. Okay, so if you encounter this problem, so based on experience, you should have always v naught equals 0 if an object is fired horizontally. Okay, so do not forget that v naught y is equal to 0 if it is fired horizontally, or it has only an initial velocity along x. Now, so we have, let's check where it involves y and v naught y. Okay, so let's find equation that involves y and v naught y. So in our problem, we don't have the final velocity, so this is x. This one we have v naught y and y. Yes, this is correct. This one we don't have final velocity y, so this is x. This one we have y, but again we have no final velocity. Sorry, it's not included. and this one is not. So we only left with this equation because we are given with initial position y and final position y, and initial velocity along y. So we are not given with final velocity y. Okay, so we'll have equation y equals y naught plus initial velocity y times t minus 1/2 gt squared. Okay, and our velocity along y is 0, so this one is 0, and our final position is equal to 0, so this one is 0 equals 300 meters minus 1/2 gt squared. So our unknown is time, so we will rearrange to solve for time. So t is equal to, so I'll transfer 300 to the other side. It's negative 300 since both of them is negative, so I just make them positive. Okay, so t squared is equal to 600 meters, and I'll just multiply 300 times 2 over the gravity, okay, or over the 9.8 meter per second squared. So our t is just square root of 600 meters divided by 9.8 meter per second squared. So using your calculator, you can solve this equation. Okay, square root of 600 divided by 9.8. So we have 7.82 seconds. So 7.82 seconds. Okay. So that is our final answer for this letter A. Now, our next question is, how far does it travel horizontally? So when we say horizontally, there's only one equation for that. And the equation for that is this one. Okay? So meaning our range is just equal to x equals bx times t, and the value of this t is what we solved previously. Okay, so meaning meaning x is equal to the initial velocity along x is 60 meter per second. So we have here we have v naught x. So we have here v naught x equals v 60 meter per second. So 60 meter per second times time, which is 7.82 seconds. So that is the maximum range. Okay. So I'll just multiply this one by 60 meters. So the range is 469.4 or 469 meters. Okay, so we'll just use three significant figures. Okay, so that's easy.